So what if you want to get even more clever as the attacker? So the firewall is now keeping track of TCP connections. It's reassembling packets that are out of order. So our little OROT trick is not going to work like we saw earlier. So here's another trick that an attacker can use. And it uses some things that I don't know if we've talked about, so I'll just spoil it. So IP packets have a field called time to live. If you haven't heard about it before, it's how many hops the packet can take across the network before the packet is dropped. This is useful, for example, if your packet somehow has an error and it gets stuck in a loop. We don't want the packet to just get forwarded from A to B to C, back to A to B to C forever, because that's going to waste everyone's energy. So eventually, that time to live is going to reach 0, and the packet is going to get dropped. So it's just a limit to avoid packets looping in the network infinitely. So that's one fact that we'll use in our attack. The second fact that we'll use in our attack is that you can usually predict with pretty good accuracy how many hops are between you and a server. And the way that you do that is you send a packet with TTL1, which means it can hop once before it's lost and dropped, and see if the server responds. If they don't, the server's not one away because they didn't respond. The packet got dropped. Then send a packet with TTL equals 2. That means the packet will take 2 hops across the network and then get dropped. If you don't get a response, that means the server was not 2 hops away. So try it again. Make a new IP packet. You, as the sender, can fill in this field. So fill in TTL equals 3. Send it, see if they respond. Send another packet with TTL 4, 5. And let's say that the first packet that you get a response for is TTL 17. That means that the server is 17 hops away. If you sent a packet with limit 16, the server didn't get it. It traveled 16 hops and then got dropped. But if you send a packet with TTL 17, it reached the server, and they sent you a response. So these are the 2 facts that we will exploit. One is that packets have a limited number of hops across the network before they get dropped. And the second is that the attacker can usually predict how many hops away the server is. So with all of those pieces of background information, what if the attacker sends a bunch of packets that look like this? First, we'll send a packet with the letter N. Sequence number is 4. TTL is 16. If we assume the server is 17 hops away, this packet will hop across the network, reach the firewall, but then it'll get dropped because it's not going to reach the server. The server is 17 away. This packet has limit 16. So the firewall sees N, and now the firewall has to remember that it's seen N. Then we will send R, and the key idea here is we will also send R with sequence number 4. So both of these have sequence number 4. That's the little trick here. And we'll send it with TTL 22, a bigger number. The firewall sees R, and now it's getting kind of confused. It sees N, and it also sees R, and they're both numbered 4. So the firewall's a little bit confused. It's not sure what's going on. But this packet R will reach the destination because TTL 22 is enough hops to reach the server. Then we'll send O with sequence number 5 with TTL 22. That's going to reach the server. And maybe you see where this is going. But then we'll send I with sequence number 5 again, and TTL 16. That one doesn't reach the server because TTL is low. But the firewall will see it. So by the way, here we're assuming the firewall is fewer than 16 hops away, so it's receiving everything. Then we might send O, and that reaches the server. We send C, E, those don't reach the server. And we send T, and that reaches the server. So we've exploited the TTL field so that the firewall receives all 8 of these letters, but the server only receives 4. The server only received the R, O, and T with sequence numbers 4, 5, 6, 7. It reconstructs those to get root. However, think about what the firewall sees. The firewall sees 2 letters with number 4, both N and R. Then it sees 2 letters with number 5, and 2 letters with number 6, and 2 letters with number 7. If you're the firewall running TCP and you're trying to reconstruct what the original message was, what letters do you even use? Is it like N and then O and then C? Well, I'm not sure, right? There's all these different choices at each sequence number. So the firewall is going to get confused. It's not sure what's going on, and it's going to have a hard time picking out the letters R, O, O, T out of this big jumble of packets. So this is a little clever trick that attackers might use to try and get around the firewall restriction. And we exploited TTLs to make it happen. So once again, the firewall is going to have a hard time figuring this out. If you think that maybe the firewall notices that some have TTL 16 and some have TTL 22, maybe it can use that to help, and maybe it can drop the ones with TTL 16. But this is pretty difficult because these numbers aren't always going to be this nice. Maybe the attacker doesn't just use all 16s and all 22s. Maybe they switch it up and use a bunch of different numbers. Then the firewall has no idea what's going on and how to pick out the packets that actually arrive at the server. Also, packets might take different routes, so the TTLs aren't guaranteed to always be the same. So we can't just use the numbers 16 and 22 to help us. Those could be different as well. Maybe the firewall tries all exponentially many combinations of letters. So it tries N, O, O, E. OK, that's not root. Then it tries N, O, O, T. OK, that's newt. That's not root either. Then it tries R, O, O, E. But if this firewall had to try all that, that's an exponential number of things it has to try. It might not get through all of those in time. And the firewall could also try and predict which of these packets will reach the server, but that's pretty hard too. So basically, to make a long story short, this is an attack that the firewall will have a pretty hard time defending against. Even if it's stateful and reconstructing TCP connections, attackers can still try and evade the firewall.